Hello, in this video we're going to look at taking a multivariate random variable and transforming it to a multivariate uniform random variable. I'm in multivariate mode, and so that's why I'm doing this video. Plus I'll need this result if I ever decide to derive the Wishart distribution, and it also will go in my playlist that I call transformation. So let's, the result is if you have a multivariate normal distribution with mean 0 and variance I. Actually, this can be anything as long as they're independent. So the off diagonals have to be 0. The diagonals can be a constant variance, but without loss of generality, we're just going to assume it's 0 with the identity matrix. Then the density for that is this, and our transformation is this, where it's the original x and then it's divided by x transpose x, you know, the square root of that. And then we want to find this density, and based upon the title that, you know, this is going to be a uniform random variable, which means constant density, which to me is kind of interesting in itself. Well, I want to give you a quick background. This has nothing to do with multivariate normal, just finding a density. So let's assume f of x is this distribution where it's kind of bumpy and then it's constant from c to d and then it goes up. And we want to find this density, this distribution, f of x, given that x is between c and d. And really, when you say f of x, it really means the probability that the random variable equals, you know, the script x, given that we're between c and d. Now, looking at this graph, that's a constant probability. So no matter where this x is in here, it's the same value. It's a constant value. Now, in the original x, let's say that value is k1. But this density, see k1, you know, if you integrate it from, you know, over this region, it's not 1, so it can't be a true density. But this k1 plays a part when you find the normalizing constant out front. So I think we can just see the graph that this is going to be some constant value k2. And the way you find k2 is you take the height of this constant value, call it k1, and then divide it by this region or this area. And it's a square. So you take this side is k1, this side is d minus c. So that's the denominator. They cancel, and it is 1 over d minus c. And you can kind of see that if we're a random variable between these, let me rephrase that, a uniform random variable between c and d, then all of us would go, duh, that's the, you know, the density value, because it, you know, it would integrate to 1 over that region. So remember this kind of simplistic example when we get into what's, you know, a little more complicated. So initially we're going to look at the bivariate case, which I think will help motivate the general case. We're going to let our random variable x be this vector, so I should make that an x, and of course my pen goes out at that time. So that's x, it's multivariate normal, 0, 1. We want to find the density of y, where y is defined like this. Now, before we find the density of this, let's first examine this conditional density. So we want f of y, given that this is r. And this is the denominator. And so really this means that the length of the x vector is r. So this really means, you know, the probability that the random variable y is equal to script y, given that we're in this case. So the goal that we're going to do here is first we have to find where all these little y vectors exist. We have to find the region that they live in. And if we note that the length of x is r, right, because we've made it this is the Euclidean distance, so the length of x is r. which implies the length of y is 1. So if we look at the length of y, so this is a constant, so we factor it out, and then we find the length of x, which is this. Those cancel, and it's 1. So given r, y has a length of 1 in two-dimensional space. So if this is the density, and I didn't know how to draw this real well, so this is our x-axis, our y-axis, and then over the top of this we have the standard, or the normal distribution. So these humps kind of, I wanted to show that, if you, whatever direction you look at it, it's humped. So these would be like a marginal distribution. And the random vectors, little y, all have length 1 in any direction. So they live on this circle. Okay? And in the normal distribution, that is what's called a contour. It's a constant probability. So given r, this is a uniform distribution. It's constant on this. Any y is going to have the same probability. Okay? So we know it's a constant. So how did we find the density of this? We took the height of any point around that circle, which is this, and then we have to find the area of that. And so, on the plane, it's a circle, but it comes up until it touches the normal density. And so it's like a cylinder. And to find the volume of that cylinder, it's the circumference, which is 2 pi, times the height, which is this vector here, or this density. It's that value. Well, those cancel, leaving 1 over 2 pi. So given that the length of the x vector is r, what's the density of y? Well, it's 1 over 2 pi. Now, really, we could stop here and say, now we know the distribution of f of y. And you can say, look, whatever value of r, the density doesn't depend upon it. This conditional distribution doesn't depend upon r. So we can really get rid of r. And that says the density for f of y is actually 1 over 2 pi. And that's the answer. But I'm going to put just a hair more mathematical rigor around that. So this is the density we want to find. And you get my thought process on this. So what we do is we introduce a new random variable. Remember, x transpose x is a chi-squared, but then you take the square root of it, it's a chi distribution. So we introduce a chi distribution and let it equal r, integrate it over all possible r's, which means we integrate it out and we're back with the original density. So these two values work, but the joint distribution can be thought of a conditional, the probability of this, which this is a chi random variable, and then the probability of y given, r. Well, on the previous page, we learned that this is a constant. So it can be factored out front, and that's what this is. So this was 1 over 2 pi. But here we're just integrating a chi distribution over the range of the chi distribution. And since the chi distribution is a density, this is equal to 1, which says that's our answer. Now here's a note that this is what's called a uniform distribution over the surface of a one sphere of radius 1. Now one sphere is a circle in 2 dimensions, right? The circle is a line, and a line is one-dimensional. So that's why it's called a one sphere. But a one sphere lives in 2 dimensions. So that can be confusing sometimes. So now the general multivariate case, so let's say x is a multivariate normal with k variables. So this is a k by 1 vector. Mean zero covariance matrix I. We want to find f of y, which is defined the same way, but now these vectors are longer, So we want to note that given r is equal to this, y lives on a k minus 1 sphere with radius 1. So the length of y is 1. So if you take, the length of it, this is a constant factored out, and then you take the length of that, which is the square root of x transpose x, which those cancel, and it's 1. So it's always 1. So this vector can go around in space and be anywhere, but it has to have a length 1, and that creates a sphere. And since we're in k dimensions, it actually creates a sphere in 1 less dimension. So it's a k minus 1 sphere with radius 1. Now, let's let O be a rotation matrix. So then the length of y, which is this, and then we multiply x by the rotation matrix, which it preserves the length. So the length of this vector is the length of this vector. But this bottom part here, when you put the transpose in, the O transpose O cancel, leaving just x transpose x. And then the top is the same. So the length of this vector is actually the same length of this vector. And we know that the length is 1, okay? But since the multivariate normal density with independent components is what's called rotationally invariant. And actually, now that I think about this, I'm gonna do a video on this showing that the multivariate normal is rotationally invariant. Which that means is you take f of a vector, that's equal, that you get the same value, the same formula if you rotate the vector with the rotation matrix first. These two values are the same. That's called rotationally invariant. But since they're rotationally invariant, that says f of y and f of oy are equal, right? Because it doesn't matter if this is the same length as this, and so if we put those in our density, it actually you get the same value because whether no matter what direction you go, they're the same. And so that says that since any direction we go is the same, then it has to be uniform. Okay, so now if we look at this density, and this is what we want to find out. So we introduce a chi distribution integrated over all possible values, and then that essentially removes it, and we get this back. But when we do this, then we can look at the conditional distribution of the chi random variable, and then y given r. But this right here is a constant. It's actually, and the way that you would find that constant is you take the value at y, which would be f of y, and then it's divided by that area, the surface area where y lives, which is a k minus 1 sphere. And so you need the surface of that sphere, and that's what this is. So this is a constant of this value. Now, since that's a constant, it can come out front, and then we're integrating a chi distribution over the range of values that it can assume. Since it's the density, it's 1, and we're left with this. So you invert and multiply. So what's interesting, and that's it. So that's it. It's a uniform distribution and with this value. But this right here is 1 over the area of a sphere. So this transformation y of this is what's called a uniform distribution over the surface of a k minus 1 sphere of radius 1. And as mentioned earlier, this derivation is going to be used in the development of a Wishart distribution if I ever get there. Well, hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.